Good morning, everybody. Can you hear me pretty well? Okay, so as Evelyn just said, I work for the Sustainable Energy Authority of Ireland, and we are a government agency that reports to the Department of Environment, Climate Action and Communications. So we work with government, homeowners, businesses and communities to create a cleaner energy future. So the role of SEAI is to support Ireland in the move towards a low carbon energy future. And what that means is we need to use less energy. And when we do use energy, it needs to be clean, or in other words, renewable. So energy needs to be environmentally sustainable, secure and affordable. And we need to develop new solutions to meet our energy needs. So the government's policy is laid down in the Climate Action Plan that was published in 2019. That's an all-of-government approach to climate action. Now, the area that we're going to focus on here today is the built environment. That's a section in the Climate Action Plan, the built environment. So this is a pathway to, reaching net zero basically by 2050. So the government is looking to upgrade 500,000 existing homes to a BER rating of a B2 or achieve the carbon equivalent of that. So what we need to do is we're saving carbon and we're counting the carbon savings. And what we need to do is the equivalent of bringing 500,000 homes to a B2. The government also wishes to see the installation of 600,000 heat pumps in Irish homes, so 200,000 of those in new build and then 400,000 in retrofit, which is the area that concerns SEAI. And for your information, 50% of homes in Ireland have a BER rating of D or lower and will require significant upgrades in the future. And to date, SEAI has supported over 450,000 homes and homeowners, property owners, owners of residential properties on their journey to upgrade these buildings. Okay, so how is energy used in the home? So some of you may know this, some of you may find this surprising, but so first of all, houses and homes in general account for a quarter of all the energy consumed in Ireland. So that's why it's such a big focus of our attention. And 80% of that comes from heating the home. So we're talking about heating the home to keep you warm and also heating hot water. And the rest is only 20% is down to things like cooking and lighting. But basically the big challenge is around heating. So how do you lose heat? So once you've heated your home, you've had your heating running a couple of hours, how are you actually losing heat? Well, 60% of it is lost through the roof and through walls, 20% through the floor, and another 10% through doors and windows, and 10% through air infiltration. That means sort of cracks in the building, but it could also be ventilation, which is also very, very important for good health, for good air quality. So what are the benefits of a home energy upgrade? Well, number one, comfort. So if you upgrade your home, you'll end up with a very comfortable, warmer, cozy home. You will save money on your utility bills because your bills will be lower. You will be doing your bit to protect the environment, and that's actually the piece that interests the government most and interests SEAI most. That's why we're doing this, and that's why there's so much money being put behind it. And what's also very important for all of us is the fact that you'll be improving increasing the value of your home. Now, how do you go about upgrading it? It can be confusing and daunting for people. So we've broken it down into 3 steps, which we called assess the home, insulate the home, and then, exchange your fossil fuels for renewable energy. What does assessment mean? So half the homes in Ireland already have a BER cert attached to them. So that's a very good place to start. Look at your BER. But if you're one of the people who doesn't have a BER certificate already, go to a BER assessor. They will tell you where you stand, what's the status of your home, what your BER rating is, and give you advice on the journey to a B2. So we prioritize insulation. So we call it the fabric first approach. So the fabric is the external envelope of the building. So what we're saying is, first step is to insulate your home to keep the heat in. And that you're reducing your energy demand, right? You may need to replace old windows and doors to improve insulation as well. And this is an example of the kind of grants that are on offer. So up to 1,500 for attic insulation, up to 1,700 for cavity wall insulation, and the maximum grant, single grant you can get is 8,000 for external wall insulation. And then when that's done, we recommend you address your heating system. So that means replacing an oil boiler or a gas boiler with a heat pump. Or later on, there's the opportunity for district heating, but that we're not actually quite there yet. So what other forms of renewable energy are solar electricity, so rooftop solar, and also solar thermal for heating your hot water. So SEAI has 3 programs on offer to the public. They're listed here side by side so that you can compare. The one on the left is the fully funded energy upgrade. So that's available to people in receipt of certain categories of social welfare payment. I'll come to that in a second. And the whole process is managed by SEAI. SEAI pays for it all. The second opportunity is then for people who want to do a complete makeover of the home. So let's say you've got a young person or a couple, or they're buying their first home and it's in need of complete renovation. They may also have a budget to spend, so they might have 30, 40, 50,000 to spend. You can do all of these upgrades in the one go, and the grant support is very attractive. So it's, it can be up to 45, 50%. Now, that's not an option for a lot of people. A lot of people prefer to do things over time. We call it the step approach to upgrading your home. And they are the individual energy upgrades. A lot of people know this program as the Better Energy Homes program. So it's like a menu of options that you can do all together or individually. Yeah, and there's just a list so that you can see what's on offer. So the most comprehensive offer is from the one-stop shop service. So that means you do it all at once. And to incentivize people, because it's expensive and a bit more arduous, the government actually gives some support towards even windows, which is not available under the individual energy upgrade scheme. Now, some people might wonder at that, but the reason is because actually we have to prioritize where the high carbon savings are, and the carbon savings are really with insulation and with heat pumps. You don't save that much with windows, and a lot of people already have very good windows anyway, because windows are attractive, so a lot of people will spend that money anyway, whereas the government tries to incentivize people to do the invisible work, the hard work that they wouldn't normally do. So that is a simple explanation for that. Yeah, here's some more details on the fully funded, and just looking at the time, fully funded energy upgrades. So if you're in receipt of fuel allowance, one parent family payment, family income supplement, domiciliary care allowance, job seekers or disability allowance for more than 6 months, and you have a child under 7 in the household, or carers allowance, and you live with a person being cared for, that will give you the eligibility to apply for this grant. And with the one-stop shop service, you'll go straight to a one-stop shop. The names of those are listed on our website, and they will perform a home energy assessment and take you through the process. So that's an overview of the kind of grants available. I won't go into them at the moment because it would take too long, but you can view them on our website or in our brochure in the Assembly Hall. And here's some additional information on individual energy upgrades. So basically, this program is available for homeowners and landlords, so it's not means tested. The one-stop shop service is also not means tested, so it's available to any of you for your own homes, for holiday homes, or if you have a rental property, because we're very keen to get, for renters also to enjoy the benefits of an upgraded home. So those grants are available to landlords. And you manage the grant application yourself. You can apply online, you get grant approval within minutes, and then you've got 8 months to complete the works with the contractor, who must be registered on our website. And there's a list of the type of grants that are available also. Yeah, so final slide. Over 450,000 people have already completed some form of energy upgrade using funding through the SEAI. And the advantages again for you are you will make your home warm and comfortable, you'll help cut energy bills, you'll increase the value of your home, and most importantly of all, you're doing your bit to tackle climate change. Thanks very much.
Great. Thank you, Emer. And she'll be joined by her colleague Ronan Sinnott actually in the assembly room and be able to answer more questions. And we also have 2 one-stop shops, which Emer referred to. Core Retrofit and Electric Ireland Super Homes are also going to be there. So it's a great opportunity to find out the details and particulars for your own homes. Our next speaker now is ABGC Architects. It's Gearóid Carville, and he's going to talk about home energy upgrades and renovations in homes. So thanks, Gearóid.
Hi. You have to excuse me, I'm going to work between two monitors, so I might lose myself on the left and catch up on the right. So that's me. And that's lovely. So we're a Dublin-based practice, and much of our work concerns adaptive reuse in both residential and commercial areas, heritage, hospitality. So it's a pretty broad base, and we've incorporated environmental methodology into our design process. So we use a number of software packages for simulation and calculation of environmental design. But the SEAI asset rating tool, DEEP, is a very useful application and simple assessment tool that we use in a lot of our projects. But and hopefully you'll see a lot of this, us collectively, the speakers, you're going to hear the same points. But like one of those points is in terms of a strategy towards refurbishing domestic houses, it's fabric first. It's your walls, floors, windows, and ultimately you're trying to get this thing called the heat loss indicator down below a 2. And after that, it's your services, your water use, heating controls, and after that, the finishing thing is renewables. You don't start with putting the PV on. You try to limit the what the house is consuming first before you start with before you go into renewables. So it's and behind the DEEP is a simple spreadsheet. So every tweak in these data changes the outcome. And so, like, I mean, this is the sort of thing we do where we're using DEEP and we're analyzing the impact of every change on the ultimate result. So it's a simple list. You know, you upgrade a wall, the consumption of energy goes down, the production of carbon dioxide decreases, and so, but it's behind this. In this Kimmage house, which went from a G to an A3 rated home, external wall insulation, double glazing, robust detailing. And so in its execution, we paid particular attention to the selection of the external wall insulation because we wanted to match the detail of the existing housing estate, which was a smooth render banded with panels of pebble dash. So the energy targets are, I suppose, an extra layer of the design process. They're not replacing any part of the service. So you're still thinking about architecture. You're still thinking about how things look and arrange and function, turning houses into homes. This house follows a similar specification. It uses a mechanical heat recovery ventilation, and when the improved air tightness is resulting in an A2 BER. And the existing house had a thin extension extending down the garden, sitting in the sunny aspect of the site. So we removed this and focused on the conversion of a garage. This is they're the survey drawings here. So that upper right bit there, that's the garage. And then we subdivided that to create home office utility storage and a WC and a slightly modified ground floor layout. And then we also demolished 3 chimney stacks in the house, which increased the internal area without an extension, obviously, and allowed for flexibility of planning bedrooms, and also allows include an ensuite at first floor. So this is now a carbon-free all-electric home. And to achieve these higher standards, we've new sort of quantifiable methods as we're moving beyond visual inspections and does this look right, to thermal imaging and air tightness testing, which we use in every project, and it helps ensure the quality standards and helps us focus on details where we need to improve from project to project, like door thresholds and the specification of flow and return pipes in our air to water heating system, as well as equally important unintended lapses of concentration from our good friends, the building contractors. So the third most important element is post-occupancy evaluation. So these crazy graphs are my fuel bill. So on the left, you'll see my usage of electricity from the winter to the summer months. So I go on holidays, I switch off the heating, pull out all the plugs, and then on the right, you see I got the highest electricity bill so far this year. So that's unfortunately the situation we're in at the moment. But the next question is the house performing as the energy rating suggests it should? And so that's why analysis of electricity bills are really useful. So in my case, I say, well, I make an estimate of what the 12 months electricity will be, and then compare that to my energy rating. Energy ratings don't include for plug loads and your washing machines and fridges and so forth. So I make an estimate on the average fuel use, and then I see, well, hold on, is my house performing the way it should be? And if not, maybe I need to get someone to put a sub-meter on my heating system or on the mechanical ventilation unit to see if something's not behaving the way it should be. So the and so it was a question asked at a recent conference I sat at, a room full of architects, and they were all asked, did they know what their annual consumption in kilowatt hours was in a year? About 15% did. I don't know if I won't do a raise hands. So this is a different aspect of things we're looking at, which is building itself and its impact on site and its impact on open space. So in this project, we had an existing cottage, a 40 square meter extension that was end of life, and the client wanted to move it to a sunnier part of the garden and rebuild to a higher standard. And then we suggested, we got ultimate planning permission for taking that 40 square meters and putting it on top of the existing cottage, and thereby doubling the size of the garden. And then after that, it's a solid wall. So the detailing to maintain or to create a thermal envelope is obviously crucial. So there's a double ceiling in there to allow for services and allow for ventilation. And then following on from the previous, we've got a compact foam threshold, so the door is not creating a cold bridge as from the previous. There's issues with how far we can push the envelope in terms of increasing the insulation without creating an interstitial moisture risk between the insulation and the old external wall. So these are things that need to remain in balance. This is another example. This is a externally insulated an existing home. It's from the 90s this time. So that the brick you're seeing on the upper level, that's a tile. It's not a full brick. And there's a particular thing about things that happen on site. There are many external wall insulation contractors only insulate up to the underside of the soffit, and it's impossible for a contractor to insulate the attic in and meet that insulation. The only way to do it correctly is to remove the first 4 rows of tiles from the outside to get the insulation in place. So you're connecting the attic insulation with the external wall insulation. So stuff like that is important. And so not all houses, though, can be externally insulated. So this is an example of the 1910 red brick. We do our simple deep review because the decorative nature of the interior, internal insulation, and because the decorative nature of the exterior, the external insulation is not feasible. So when we do our simple deep calculation, we're not getting a heat loss indicator below 2. In fact, it's 2.8. So it's not going to be eligible for an air to water heat pump grant. But when we do the calculation using our simple deep tool, we can see that actually using an air to water system, it actually will achieve a better energy rating and produce less carbon dioxide than a gas boiler for the same specification of building works. This is an example from just showing you the impact quite clearly of what is in this case dry lining works to an older building, a 1790s terrace in Marino, which unfortunately through years of subdivision and bedsit use, a lot of the moldings and so forth weren't there. So we used an Optima system on the inside, and ultimately with a gas boiler and robustly insulating the attic, we got that to a B2, which is obviously a green mortgage. Which illustrates the impact of form in the building. Because what you're looking at is a terraced house. It's got very little external envelope, 4 stories. But regardless of the age of the building, we're drilling down into, I suppose, ever harder into existing buildings and looking at how we can retain existing fabric, modify junctions and thresholds without losing material or character. And so in that previous one, I think I found a potential little 10-15 mil space. We're doing a bit of repair work on a sash, and I found a little 10 mil space in behind that where we could potentially thermally line it with an aerogel or maybe a breathable plaster, which will reduce drafts as well as improving the surface temperature on the inside of the room. But this work needs a lot of consideration because of the risks of either partially insulating your home, using the wrong materials, or using the right materials, the wrong thickness for their technical installation. And like in this home of the former home of George Jameson, which was derelict for over 30 years and now very sensitively converted into apartments with minimal loss of fabric. We used no dry lining and focused on the occupant health through the installation of heat recovery ventilation systems, as well as upgrading the glass in the crit-all windows to slim double glazed units. And so my own research of relate in this area is focusing on the impacts of changes to ventilation and the impacts of partial ventilation, looking in this apartment in town, and where works have happened and how they've happened, and how to correctly model that existing fabric to create a better outcome when you're doing the proposed refurbishing works. So here I'm analysing different paints to see how quickly they dry out. I'm looking at the concrete to see about how breathable it is and how quickly moisture might transport through the system. And that's a beautiful picture of some mold. So that's the past and the present, and this is the future. So we know. If I was planning a new build or retrofit, I'd want to have a small notion about what's happening next. So we've even more aspirational U values. Operational carbon is what we already know about this. It's energy we consume. We've had half a dozen Part L in the building regulations in the last 20 years, and the targets are continuing to rise. More change is going to come. Embodied carbon is going to be a thing. So the CO2 or CO2 equivalent it takes to make a product, bring it to site, deliver it, install it, and then remove it at the end of its life is going to be legislated for. The certification scheme already exists. They're called environmental product declarations. And so life cycle assessment is going to be required for construction. We should be able to compare the impact of a cavity wall, the cost of a cavity wall, both in carbon and in euros. And as we've come to grips with the sort of sensible use of space heating, the other low-hanging fruit is hot water and being smart with its use and recovering heat from our hot water waste wherever possible. So the great benefit of this is of the healthy interior is consuming less energy and producing less carbon. Ultimately, though, we rely on two bodies. The more knowledgeable the public is, the more they will push their designers and ask for better briefs, which will have better outcomes. And secondly, I suppose we look to our legislators to continuously raise the standards at a pace that is reflective of the climate challenging that we are attempting to deal with. Thank you.
Super. Thanks, Gearóid. This event is part of Open House Dublin, an architectural festival that's been running over the last few days. So we're well represented with architects, which is great to give kind of a different perspective on how we view our homes and kind of taking different angles. And Gearóid mentioned about kind of older homes, and Bill, I said, will kind of focus on that area. But just, I said, to have more examples, could I just find out actually from a show of hands, how many people in the audience are architects or energy experts, technical people? Okay, a couple. So is everybody else and a homeowner thinking of doing an energy upgrade? Okay. All right. So just to kind of let them know how technical to go. But no, I think I said, I mean, there's a lot of information there, but as Gearóid said, I mean, I suppose it's trying to get to grips with it all and find out what's best for your home and asking the right questions. So Frank, if you want to join us now for your presentation.
Thank you very much. Over the past 20 years, we've been evolving our thinking and our processes for energy upgrades and historic fabric. 2006, we took a little stone pavilion and we did an experimental project to try and bring it to passive house insulation standards, air tightness, a lot of external insulation, membranes, tapes, and so on. 2011, the project in the top right-hand corner, this house is 2-story, 1-story over basement. It had been dry lined and the dry lining system had failed. We used a proprietary dry lining system, used a lot of, again, using intelligent membranes or breathable membranes extending from basement to roof ridge level for breathability, insulation, air tightness, simulating it using WOFI and Therm and working with people like Andy Lundberg. That building also has an extension to the rear, which is timber frame highly insulated, highly airtight. But the project we want to speak about in more detail is the project in the top left-hand corner. This is a protected structure. It's in Thomastown in Kilkenny. And you can see on the left-hand side, there is an archway into a courtyard at the back. Underneath that archway, there is a stream running through into a little river that runs down the street in front of the house and floods. So the drawing shows is the building in the context of the urban grain of Thomastown. House, when we came to the project, planning permission had been granted to convert it to 2 apartments, one on the first floor, one on the ground floor for Camp Hill communities. Courtyard at the rear contains 2 new build apartment blocks, timber frame, highly insulated. So this is the courtyard at the rear, really tight, south and west facing courtyard. The photograph on the left-hand side, the entrance to the courtyard is actually underneath one of the apartment blocks. So when we, having worked in energy upgrades of fabric, historic buildings for quite a while, we'd been thinking about, or we've been involving our thinking in relation to what is proper sustainability. Particularly, Gareth has already mentioned embodied carbon, embodied energy, and the importance of retaining as much fabric as possible. Because what we were finding was, in order to achieve energy upgrades, we were losing massive amounts of original historic fabric. Now, these are not buildings that are, you know, let's call it grade 1 protected structure, listed buildings or whatever. These are the sort of the meat and 2 veg of many of our small towns and our city streets. So this top left-hand photograph shows what the roof was like, weeds growing out through it, slates missing. So what we did was retain the existing rafters, put in new timbers, spliced in timbers, retain the lath and plaster ceilings below, fix the wall plates, put an air tightness membrane draped over the top of the rafters, used fiberboard, timber fiberboard as insulating materials, fiber put in between the rafters. So we're creating a warm roof. Since that, we've evolved this into using pumped in cellulose and so on. The roof, the detail on the top right-hand corner, you can see the build-up. The build-up is natural salvage slate on double battens, very important. On a membrane that we're told is not required, it's a breathable felt, but risk, we were going better to include it. On fiberboard, on insulation, on air tightness, with retained lath and plaster down below, and lime plastered chimneys and so on. Internally, the roofs had been leaking for 20 years. A lot of the lath and plaster ceilings were still in place, so we used little circular metal discs to tie them back up. Fixed up the lats in a number of places and patched in the plaster. I'll speak about services in a few minutes. You can see the great big woven pipe coming down through the ceiling. So again, patching in using lime plaster. In this photograph, and I'll speak about it later, on the bottom photograph you will see the dry lining of the internal walls, where we're using a calcium silicate board that is compatible with the fabric of the original building. We have since evolved, partly for cost reasons, how we insulate external walls. We're now using lime plaster with cork in it that improves the thermal performance while being compatible with the fabric that's already there. External walls, very poor condition, replacing timber heads. We tried to keep timber heads where at all possible. In this case, they had seriously deteriorated. Great big cracks in the walls, stitching them together with pieces of stainless steel, trying to work with engineers who are understand these buildings and understand how these buildings work. You can see the insulating of the walls using calcium silicate board, and the finished article with retained fireplaces, sometimes using fireplaces for ventilation and so on. This relatively simple building, stairs in the middle, 2 rooms either side at ground floor, 2 rooms either side at first floor.
Sorry, Bill.
My apologies. Oh, I'm sorry about this. Sorry about that. Right. So this building has a stairs in the middle, 1 room either side at ground floor of the stairs, 2 rooms either side at upper floors. The internal cross walls are made out of timber frame with brick infill and lime plaster. Where they touched the ground, they had deteriorated, rotten. So we supported the existing walls, put in new timber, put in new floors. Again, windows, all the boxes, well, there was some historic glass which we found, which was great. Retained that, reused it. Sashes were taken away, had to be taken away, but they were reused. Boxes, weights, all of that conserved, keeping as much fabric as possible of the window frames, and lime plaster externally, and it's lined because that's what was on the building previously. Beautiful little porch. This is really interesting because there's actually a step down inside into the building. Step down about 400 mil, so the road externally is higher, and real fun working with a brilliant craftsman to conserve, restore this. We even managed to insulate the roof of it. I'd mentioned that the buildings internally is lower, so risk assessed it. The street floods in Thomastown, or had flooded in Thomastown, so controversially, possibly, we tanked the walls to a height of 1.5 meters at ground floor level. So you can see here where we're using a Platon membrane, letting the water actually come through the wall, using radon barriers, blues, and so on. And services. This building, when we got to it, it had planning permission granted for an apartment at first floor and an apartment at ground floor. So the implications of that were fireproofing, fire separation between ground and first floor, acoustic separation, and how you run services in a relatively small, modest building. We looked at going back for planning permission to change the layout to stack apartments left and right, but there was a decision made not to do that. So we had to, there was beautiful stairs in this. In the bottom right-hand corner, you can see where the contractor came to site and he enclosed the stairs in plywood and kept it. But we used a proprietary system at first floor level to get our energy up, or to get our acoustic upgrades and get our fire upgrades. We took all the services where possible out of the floors, and the walls to the stairs, we built a new certified fireproofing wall on one side. And in order to do all of that, this is one of the pages of all the details it takes to work something that complicated out. Services, again, we tried to run them where there were already holes in the ceiling. See the services in the ground, we have underfloor heating. Do a lot of latest thinking in terms of residual heating requirements is heat pumps into buffer tank storage running on night rate into underfloor so that we can run the heating circulation at low temperatures, 40 degrees rather than typically 60 degrees for RADs. Model, this is what it looked like when we got to it. 2-story little house, yard at the back, the remains of an old coach building with an arch through to it. We put in 1 block at the back, simple ground floor apartment, first floor apartment, timber frame, highly insulated, highly airtight. Put a 2nd block into, contained within the walls of the former coach house, and raised it up onto pilotis with beautiful exposed board mark concrete, whether you consider that sustainable or not, where you move in underneath it. So thank you very much.
Thank you, Frank. And our next speaker is from our consultants, Bill Hastings, and he'll also be focusing on older buildings, obviously from a conservation point of view. Again, just from a show of hands, how many people have older style homes? Yeah, quite a few, about half or so. Yeah, it's sort of the nature of this county. And then our final speaker will be a homeowner. So Bill, if you'd like to join us, yeah.
Okay, yeah, up and down. Hello, can you hear me? Yeah. Okay, my name is Bill Hastings. I work as a conservation architect. I mainly give advice rather than actually do any on-site stuff. So I'm going to talk more generally than Frank or Geroid have, talk about sort of principles. So let's see how this works. Yeah. So if you want to improve an historic building, you need to understand it. And I think both the architects who've spoken have indicated that they do understand historic buildings. But there are a lot of people out there that don't, and some of the insulation methods, some of the other methods that are used in modern buildings won't work necessarily in historic buildings. There's a very interesting report that was published 4 years ago. It's called Deep Energy Renovation of Traditional Buildings. You can find it online. And as you can see, the SEAI were involved, the Heritage Council, Kerry Conservation, who are a specialist conservation company, and ICOMOS, the International Council on Monuments and Sites. And so it has some interesting principles in it. So the first thing is, how do historic buildings work? And for this, I have taken the example of a sort of typical terraced house that you might find here in Dún Laoghaire or elsewhere. And there are, certain things about these buildings that, are common. Firstly, initially, the timber framed roof, but usually uninsulated. Heavy masonry walls. That's perhaps the most distinguishing characteristic of historic buildings, is that they've got thick walls as compared to many modern or 20th century or even 21st century buildings. Timber single glazed windows is common. Timber floors, and often a solid lower ground floor. Yeah. So the question then is, were they warm? Well, they could be warm. The expectation, I think, in a building built in, say, 1850, of the internal temperature wouldn't have been that you got, summer temperatures like 21 degrees all year round. There would have been an expectation that people wore clothes in the winter that were appropriate. I have sometimes suggested that the best insulation for a historic building is a three-piece tweed suit. Anyway, the heavy masonry walls, they were better at insulating than anything else that was available. So people built heavy masonry walls because of that. The single glazed windows, they were okay if they were maintained. The difficulty is over time they become somewhat worn, and they get a lot of drafts around them. And Frank had some interesting pictures of up and down sash windows. And then quite often the fire in the main rooms on the main floor would be lit relatively early in the day. When I was a small boy, I lived in my granny's house, and that's how it worked. It was a house built in the 17th century, not the 18th century. But in the main rooms, the fires were lit sort of 10 o'clock in the morning. So there was a kind of low grade temperature increase all the time. And then at the lowest level in the house, certainly there would have been a range. And anybody who has a range or an AGA or one of these things will know that these things keep the house warm. Now, one of the important things is thermal mass. Thermal mass was mentioned by the other two architects. And if you have a heavy building, it's important to keep the temperature reasonably up all the time. Now, reasonably up might be only 10 degrees, not 20 degrees. But, you know, as long as you can keep the thing warm, the walls do a bit of work for you. So you probably can't read that, but this thing's going to be up online, and so you can read it anyway later. But that retrofitting report, published, as I said, by the SEAI and the Heritage Council, etc., it makes some important points. And the first is that thick walls, the rain hits them on the outside. The walls are thick enough so that the water doesn't come the whole way through. But that depends on evaporation. It depends that on the wall being able to breathe so that water can evaporate from it when it's not raining. One of the things that this report points out is that moisture in structures is very important. That if your wall is wet, its ability to act as an insulator drops dramatically, and that it's really important for that not to happen. And so one of the first things you need to do to keep your house warm is clean your gutters, clean your downpipes, ensure the showers outside are working so that water doesn't seep into the walls. And that's a kind of very important point. The other thing that's really important is that the walls need to be breathable. So if you apply insulation inside or outside, those insulations need to be breathable. So some of the insulations that you would use as external insulation on a modern house, you can't use on an old wall because unless the wall is absolutely dry, and they usually aren't. So how did historic buildings behave? Well, this is a diagram that shows perhaps how they behaved. So the stone walls would have absorbed a little bit of water from the ground, but you might be able to reduce this if you had a French drain. And a lot of buildings did have French drains, even in towns like Dún Laoghaire here. There, you know, if you won't go looking, you'll probably find that there's a drain outside the wall, and it would be a trench full of gravel with a pipe at the bottom which had holes in it to allow water to run away in the pipe. If you had a solid floor, probably it was stone on lime mortar. So it would get a little bit wet, but then the water could evaporate to some degree. The external and internal plaster on the wall would have been lime. So again, it's something that can allow breathability. Now, what can go wrong? Well, fairly obvious things. Firstly, you could forget to check that your French drain was working or that your other drains were working, and you end up with a lot of water around the base of the wall, and that starts to climb up the wall. It doesn't usually climb through the stonework, it climbs through the mortar. Granite, a lot of buildings in this area are built of granite. Granite doesn't absorb much moisture, about 3 or 4% by weight. Limestone absorbs a lot more. Then, you know, in the middle of the 20th century, some of your original plaster might have been falling off, and somebody had a bright idea of putting cementitious-based render on the outside. So you get, you know, sand and cement mixed, and it's pretty waterproof. So it throws off more rain unless the rain is very wind-driven. Though it moves, it cracks, and little amounts of water get through the cracks and get into the wall. Now, it doesn't breathe, though. It's not vapor permeable. So if the water goes into the wall, you can't get it out. The other thing is that people put on damp-proof compounds on the inside of the wall. You know, they see a bit of rising damp, they take the plaster off, they put on a damp-proof compound, and that stops the water coming out of the wall. But the water's still in there, and it goes further up the wall. And research that I've seen from Europe, there's a very interesting guy from Belgium about this, he was able to show that it often climbed to the first floor. And then you might have used some cementitious stuff on the inside as well. So you're trapping water in the wall. So the wall doesn't really work properly as an insulator. So a lot of houses have these kinds of defects, and these defects were caused by just people, well-meaning people thinking they're doing the right thing, but it doesn't work. So what are the possible ways of fixing this? Well, you can try to get back to the original performance. So the first thing is that you use breathable plasters inside and out. Now, Frank mentioned using plaster. Well, one of it was Garroda. Frank mentioned using plaster with cork in it. You can use hemp in it as well. So you can add also aerogel, but aerogel is very expensive. So you can achieve increased levels of performance for the wall by using lime plaster with an admixture that is insulating. So you can improve the efficiency of the wall by something like 60%, which is pretty important. You then have to fix your drains. Go looking for your French drain, or if you don't have a French drain, put one in. Dig a trench around the house and put a pipe down the bottom and fill it full of gravel. Now, the most common remedial thing that's done in an historic building is on the ground floor. If you have a solid ground floor, you would take the floor up, you'd put down, go down a distance, you'd put down gravel, put down a vapor barrier, or what do you call it, a radon barrier. You'd add insulation, and then you'd put a concrete floor down with underfloor heating in it. And ideally, that underfloor heating would be run from a heat pump. And so what you're doing there is replicating the range, in effect. You're adding constant low-level heat at low temperatures. They're not coming in at the sort of temperatures that modern central heating would suggest. You're adding heat at low temperatures, but it makes a hell of a difference to how the house behaves in the long term. And other options for improvement. Well, the first thing is you make sure that the roof space above any insulation is ventilated. There's this thing called interstitial condensation, where you get a dew point within. If vapor comes up from below, particularly bedrooms where people are sleeping, people give off moisture when they're breathing. You get water forming in the thickness of the insulation if it's a quilt. So you need a vapor barrier underneath it, a reasonably efficient one. I have used double silvered vapor barriers. They're not always recommended, but they have a huge advantage in that they reflect radiant heat. So you will have seen, people sort of being dragged out of the sea and shivering with hypothermia. And the first thing they do is they wrap them in a very, very shiny plastic material or foil. And you need to do that with your house as well. You don't do it to the walls, but you can do it to the roof. And the advantage is, first of all, that it's very reflective, and it reflects the summer heat upwards, and it keeps the heat in the house in the winter. And it's also a vapor barrier, which means that moisture coming from the house doesn't get into the roof space. Get the walls dry as you can. Draft-proof the windows. You can draft-proof historic windows without any great difficulty. There are specialists who will do that for you. Install underfloor, and ensure your drains are working. Now, I can't read that from here either. A couple of things that are important to note here. Firstly, is that the actual measured thermal performance of historic walls is higher than the calculated performance. When you get a BER rating, there's an assumed value for different kinds of materials. And so there was some research in Scotland, and they found that the actual performance was higher. I know that Garrod is actually doing experiments to test some of this, and Carrick Conservation, who are one of the authors of this report, have done some work on this, testing the actual performance of historic buildings. The other thing is that some of the approaches to modern buildings don't work, and it's important. And so the that's the Department of Local Government that it was in their guidance. They suggest very strongly that you need some kind of conservation advice, because not all people who do BER ratings will completely understand the subtleties of historic buildings, though quite clearly the two architects here do. This is the end. This is the last slide. Historic buildings are sustainable and resilient, and the proof of that is they're still here, and a lot of them work very well. They're inherently climate responsive. They were built to be. I mean, they were built as shelter. They were built to be the best thermal performance available when they were made, and we should use that. They are built with low with materials that have low embodied energy. Now, that's most important. Both speakers before mentioned the question of embodied energy. If you go and are going to put insulation on the outside of your house, and the insulation is petrochemical, and it uses a huge amount of energy to manufacture it, then you're creating a lot of carbon. Your carbon footprint is very high. So a lot of modern materials have a high carbon footprint, but things like timber floors, stone walls don't. And so historic buildings are entirely positive from that point of view. And then, of course, the thermal mass is very important if you can make use of it. I live in a single story house that was built probably around 1800 down the road here. And when we first moved in, we couldn't afford central heating. So we got a stove. We put the stove where the return, which is 18-inch granite walls, meets the main house, which is also 18-inch granite walls. And this stove, was run all day, and it heated the structure, and the house was never cold. And sometimes constant heat is really important. And one of the great advantages of using heat pumps is that they tend to produce constant heat. So the other thing is that constant modest heat is more comfortable than intermittent high levels of heat. And I have a heat pump, and my office is in Dalkey, and it's a 1960s building with a shop with a flat over it. And my daughter lives upstairs with her husband, granddaughter. And we put in a heat pump a year ago. And the thing that I find most extraordinary about it is I never notice whether it's warm or cold. We go in there and it's just normal. And in fact, the internal temperature is probably 15 degrees, not 21 degrees. But for me and for my family, they find it really uncomfortable. So thank you very much.
Thank you, Bill. And I think there's a great lesson in that, I mean, I'm not quite sure about the three-piece tweed, but certainly some woolly jumpers. There's a campaign at the moment from the government that we're rolling out as a public sector body, Reduce Your Use, about lowering the temperature in our buildings and, switching off the heat a couple of hours before, or the building's going to be vacated, and I suppose being mindful about not lighting up everything that doesn't need to be lit up and everything. So, I mean, there's lessons, I said, both in kind of public buildings and I suppose at home as well and everything. So maybe we're kind of used to t-shirt temperatures all the time, but certainly there's a lot to be said for us at dressing ourselves, not the home. So what was the phrase I found that there was, we were at an event recently, it was like, make the world better, wear a sweater or something. So I think that was it. So our final speaker anyway is Patrick Davey, who is going to tell us about what it's like to live in a warm, comfortable home, and has lots of experience to share. So thank you very much.
This was the house. What is different from what I'm going to say is that we are a new build, and that of course makes a profound difference, because you can do a lot of things that are simply not possible, or very difficult, or correspondingly expensive if you're upgrading a house of any sort. The other thing is that to some extent, I'm a bit archaic in this because we did this 10 years ago. And 10 years ago, it was very difficult to find an architect who'd even heard of the idea of building a green house, an energy efficient house, and still less was it easy to find a builder. Now, in the event, we did find both, but things have changed radically in that respect. And the other thing that has changed so much is that materials are changing almost by the minute. If you go to the energy show, which usually comes on in about February, what you see this year is not what you will have seen last year or the year before, because things are changing so fast. And that's where you need the experts who are actually doing research in this area and really keeping on top of things. However, that said, we did end up with a house which, as far as we're concerned, ticked all the boxes, and we found it very comfortable, and it suits us very well. But I'll go through, basically, we had to do the research ourselves. My wife was more concerned with the appearance, and I was more concerned with the techie side of stuff. So that's, roughly speaking, what I'm going to be saying. But that is the house that we have ended up with. That actually was taken a while ago. It's got more stuff growing up around it and so on now. It faces very slightly west of south, which is ideal, of course, for the solar panels on the roof. And also it meant, which is one of the prime requirements, that we would not, it would not be obtrusive, because we do have neighbors, and they didn't make any objections, but they were obviously nervous about what was going to happen. And when they came to see it, the common problem was, oh, it doesn't overlook us at all, because we turned it slightly away from the other houses in the neighborhood, but actually it suits the panels as well. What we wanted to do was to produce a house that was as energy efficient as possible, given what was available at the time. And we could have taken one of the passive house designs, but none of them suited the locality. And so we went really about designing it ourselves, or at least saying what we wanted the architect to do. So basically what we ended up with was a traditionally built house. It's block built with insulation on the outside. And the reason for that was that we had lived in a Victorian house, and a lot of the, yes, our insulation was sweaters, 2 or 3 of them mostly. But the solid walls, which in our case I think were maybe even 2 feet thick, did give a lot of thermal stability to the house. So what we wanted here was something which, if there was a power cut or there was some other reason why we couldn't heat it for a while, the house would remain at a reasonable temperature, and it does. So it's block built with the insulation on the outside. You might well think differently now, but that's what we decided at the time. We put on photovoltaics, 16 panels generating 4.5 kilowatts. I think now the efficiency has risen, and you'd get 5 kilowatts out of that perhaps now. We did think about water heating using panels, and our architect said no, because first of all, you'll generate so much hot water you won't know what to do with it, and you won't be able to use it. And the second thing is that there is a payoff between photovoltaics, which generate 100% green electricity on site, and the electricity which you buy in from the grid, which of course is not fully renewable. So by switching from, which one we do during the day, during the high value time, using our local generated electricity, you are actually saving about 2.5 times the carbon footprint of the basically 1 kilowatt that we generate costs nothing from a carbon point of view. Buy in a kilowatt from the grid and it's got a 30% renewable profile, and the rest of it, of course, is carbon generating or CO2 generating. So by switching the one for the other, it's actually quite a bonus as far as the BER is concerned. We use air source heat exchange. I'll mention these because probably some of them are not very familiar to you. The hot water is on a loop system. We have controlled ventilation with heat exchange, which is crucial. And the windows are wooden on the inside. On the outside, they have a thin skim, about 1 millimeter clear, of aluminium. And that is self-colored, so it never needs painting, but it also protects the wood from any rain. And if any water does get behind, there's a space where it can drain away. And as a result, you get very good insulation from the wood, but also it is protected and it should last more or less indefinitely. And we also use rainwater storage, which has not yet been mentioned. That does the toilets and washing machines. We could have put in a UV sterilizing system onto that, in which case we could have run the entire house from rainwater, but we didn't do that for reasons I may mention later. It was a new build in 2013. I think I've mentioned most of these things. The roof space is a cold space, so the insulation is at ceiling level, not above. And it's ventilated. We did have a problem because unfortunately the people putting in the heat exchange ventilation, that involves pipes around the place, they hadn't registered that the roof was a cold space. So you were getting condensation inside the pipes. That was sorted more or less immediately, and fortunately, we took the house over in the winter, so this became apparent very quickly, and they just simply insulated them. There's been no problem since. We didn't put metal foil in the roof because one of our sons had done that, and he didn't get a mobile phone signal inside the house. So that's something you need to be aware of, that some of these insulation systems which involve the metal foil will interfere with Wi-Fi and so on. Those are the solar panels. We were very fortunate because the one thing when we were putting them up that I absolutely did not want was to have the slates drilled, because I simply didn't trust any form of sealing to remain adequate forever. We waited 24 hours and we were the first house with a new type of bracket, which is now standard. And that is led in under the slates, joins onto the joists, and the weight is taken on the structure of the house, not on the slates, and you won't get any wind vibration or anything of that sort that's going to possibly damage either seals or the slates themselves. The only problem is that if there is a part, I thought, and nobody corrected me, I thought that if there was a power cut and we were off from the grid, that the panels would keep the house running. They don't, because for safety reasons, you can't have panels possibly connected into the grid when the linesmen are up on the grid, up on the lines trying to repair a fault in the grid. You don't want roof systems like ours electrocuting them. So when the grid is down, everything is off. Sorry, everything is off. So the house is just as isolated as it would be. I don't know whether there's systems now. The experts would know. I don't know whether that could be circumvented now, but it has to be 100% certain that you can't electrocute your ESB men. I don't know whether you can see this, but the bracket, the horizontals hold the panels. These brackets come in under the slate, which is cut, and it's got a particular protection system. It's got a second slate in there, and that completely seals any weather getting in underneath. And the weight is completely separate from the slate system. But that is now standard practice, I believe. The air source heating unit, the house superficially would require a 12 kilowatt unit. In fact, this is the size we were advised. It certainly performed faultlessly for the last 10 years. It is, rather than having something which comes on, pumps a huge amount of heat in and then turns off, it tends to be on a little bit longer. It runs the heating system runs at 35 degrees under the floor when necessary, which is actually not much at the time. But it's worked, as I say, absolutely faultlessly. It's an IB system, which is Swedish, and it works down to minus 30 degrees, which I don't think we're ever going to hit in this country, not now. Certainly not until the Gulf Stream stops, which maybe it will, but with climate change, but not in my lifetime anyway. So minus 30, it works at more or less 100% efficiency down to that. So, it's worked superbly well. Just a warning for any of you who might think about doing this sort of thing. Sometimes people talk about ground source heating. Personally, I can see no reason for putting in ground source here in Ireland, because the air source will always work. We're never going to get temperatures so low that it can't work. But the second thing is that, and it's much cheaper than putting in all the pipe work into the ground. But the installers told us that there were a number of systems which they had put in a year or two before, which weren't working. The reason was that there'd been a drought. This was October, and there'd been virtually no rain since May that particular year. Great for building. And what they found was that the ground had dried out, so there was no heat transfer from the ground into the pipes of the system. So they were simply getting no heating at all. So it's something you need to be aware of if that's what you're thinking of doing. From my experience, I can see no reason for going for ground source at all. Certainly not for domestic. Well, I can't say for any reason. I did hear a podcast where someone was complaining bitterly about the fact they put in underfloor heating, and the heating bill had gone up by a factor of 4. But then they let out the fact that they put very thick carpets into the house, which of course are very good insulation. So there they were generating heat under the floor, but then putting insulation over the top of it, so it couldn't get into the house. So if we're going to have underfloor heating, then you don't have carpets. The two things are not compatible. A trivial problem in a sense, bathrooms, you tend to have tiles. which tend to be cold. Now, the heating system is set up in such a way that whenever the heating is on, the floor of the bathroom is warming. The trouble is the heating is on so little, because the house is so well insulated, that the tiles are cold. And I would suggest that it might be worth thinking about, just in that room, putting an electric heating mesh immediately under the tiles. You can turn it on 5 minutes before you go for the shower, and it'll be a lot more comfortable. I mean, it's a trivial thing, but it is experience. The piping system looks a bit complicated, and of course it is, because we've got a water system, the normal one, but also on top of that, parallel with it, we've got rainwater harvesting as a rainwater system as well. So there's sort of double the amount of piping that you would expect. One thing that the architect suggested was that we put in a hot water loop. Now, as you can see, it's a bungalow. The heating system is at one end, and the bathrooms are scattered about the house a bit, but basically down the other end. So that means that in the bathroom, you turn on the hot water, and there's a long, long wait before any hot water gets through. This gets around that. What it does is to simply have a circular pipe which runs around the house. Water is circulating through that, hot water is circulating through that, on a time clock, of course, for when you need it. And then all you're doing is emptying out that much pipe of cold water. So it actually saves a huge amount of water, which you draw in, and then it gets cold again. Sure, there is a bit of heat which is going into the house, but so what? It's going to be keeping the house warm anyway. It's not being wasted. It simply is saving you throwing away a lot of water that you've spent heating. Heat controlled ventilation. This is the key to the whole thing, really. The house. The architects know what this actually means, but the leakage rate for the house, a passive house is 0.7 cubic meters per whatever. Our house is 1.07, and the building regulations say 7. So basically, it's a completely airtight house. That means, of course, that there's a danger of condensation from simply having people in the house. So therefore, you need ventilation. So what is easy enough to do in a new build, you simply extract air from the kitchens, toilets, etc., bathrooms. That goes through heat exchange. Fresh air comes in. You have your 3 air changes per hour, and you only lose 5% of the heat, because virtually all of it is trapped and brought straight back into the house again. And it works extremely well. Yeah, okay, well, I've mentioned that. The water tank, 10,000 litres we put in. The website, sizing website suggested 2,500. Being rather aware of climate change, we decided to put in 10,000, and that has gone dry. So 10,000, I would say, is a minimum. And that's with 2 people in the house, well, and visitors. Rainwater storage, yeah, well, that's it. So that's it. I mean, all I've tried to do is to give you the experience of what it's like, what we found works, and what doesn't. Thank you.
Thank you. And I'm just aware that we have the Meet the Experts part now, which is in the assembly room, and we have a number of guests joining us. I saw the Cahairlook probably saw me in her chair. Mary Hannafin, who's been a great supporter of energy and agreed to do the photocall and everything else. And I saw her at an event last week, so I'm sure a 7-day-a-week job. And we're also joined by Councillor Oisin O'Connor from the Green Party and Frank McNamara from Fine Gael, as well as 3 one-stop shops. We have demonstrations from our library staff of the Home Energy Saving Kit. Gavin Hart, who is a mentor for sustainable energy communities, of which Pat, you didn't even get around to mentioning, but he's a member of Shankill Action for a Greener Earth. And all the speakers will be joining us as well as some more architects and energy experts. So do join us now. We're moving from our 2018 council chamber to the 19th century town hall in the assembly room. So see you there, and thanks everybody for your attention.